Okay, let's roll, folks. So this is the second lecture of week one, right? As I sent out the announcement, this is just a one-off reschedule because I've committed to an event tomorrow. So we'll go back to the regular Monday 9 a.m. and Wednesday 12 noon slots from next week. So just please accommodate me for just this week. If you haven't yet looked at the website, make sure you go through the course outline. The lecture content will obviously be all here. In fact, we've already released a bunch of sample programs for you. I mean, you don't necessarily have to look at them right away, but this will be useful as we move through the course. And then some of the links I'll show you later today will also be added here. So you can always go back and look at them. The labs will start next week. For now, and of course up here you have the individual links for your specific lab. So I think in your timetable, you should have one of these lab classes. So just make sure you join the correct one. And if you miss the live lab, you'll find a recording a little later on that same day here. For now, we've released a introductory lab. So this is not really a lab exercise as such, but this is simply introducing you to the various tools we may use in this in the labs really. So just make sure you go through them just so that you're familiar with these tools before the actual lab starts. And finally, the homework questions. So these should already, now my view is a slightly different, so you won't see all of these. You'll only see the ones we've released to students, but in any case, you can start looking through these and work your way through these questions. So a lot of these are actually from past exams and stuff. So that should help you familiarize with the type of questions you might get asked on the exam. The answers for the questions here will be released. These ones, we encourage you to discuss on the discussion forum. We will help you out. So once you start the discussions, we'll chip in and say, hey, this is correct, and so on and so forth. So we'll certainly help you out. But we thought that might be a good sort of incentive for you to actually start working through the questions, right? Rather than just us giving you all the answers. So yeah, please do that for these questions here. The forum, again, make sure you're not posting anything on web CMS. I think we've disabled everything anyway, but if you don't know where to go, just follow this link. You will have to manually join the forum. So just click that. It should allow you to join, and then you can participate in the forum. Feel free to introduce yourself and ask any questions about the course, and we'll keep looking at it and getting back to you as quickly as we can. Okay, so now let's roll with the content. So a very quick recap. We start, I might just look at, where should I? Let's see. Oh yeah, here. So we started off by looking at what is the internet, what are protocols, sort of, again, remembering that this is just a very high level view. We'll be, of course, uncovering a lot of this through the course. So we started looking at the nuts and bolts view, the services, service-centric view of the internet. We briefly looked at what exactly is a protocol. Then we started looking at the structure, if you may, of the internet, starting off at the edge where we have the hosts, we have the access networks, and of course the actual links that connect all these devices together. And then we started looking at the core of the internet, right? So this is where we'll spend a bit of time. In fact, we started with this discussion towards the end of yesterday's lecture. And we talked about how there are two different approaches that could have been used to design the core. By the core here, by the way, we mean this part here, which is the interconnection of all those routers and switches. For now, we'll just refer to these as packet switches. We'll look at the exact distinction a little later in the course. So the internet uses packet switching, whereas there was another technology back then called circuit switching, which had its origins in the telephone networks. And so there was a bit of a sort of rivalry between the two, and packet switching won. And the reason it won is because while circuit switching might seem like a cool idea, that you're explicitly reserving a circuit and that way you're guaranteed to avail of whatever bandwidth you've reserved. So let's say if you reserve 1 megabits per second on this end-to-end path, then you're assured that you'll always get 1 megabits when you're sending data. Now that sounds fantastic, but there are various problems with doing that over a large global network. And we looked at some of these issues like inefficiencies, the difficulty in actually reserving a rate, because the various applications we use may not necessarily always transmit data at a fixed rate. And most importantly, the overhead that would be associated with the routers, because if all the packet switches in the network have to maintain all these circuits, it's going to take them a lot of effort and a lot of income. Essentially, they'll have to do a lot of state management, which we don't want the core of the internet to do, because really we want the core of the internet to keep forwarding data as fast as possible, right? So that's these are one of the some of the key reasons why circuit switching lost out. And then we started looking at packet switching, and the idea is fairly simple. The data is actually broken down into chunks. Each chunk is referred to as a packet. We add a certain header to the packet, and this header contains certain information that is used by the core of the internet to forward the packet towards the destination, right? So you can think of the headers as a API in a way. And then we looked at essentially what router does, and we'll of course touch on this a lot more later in this course, but broadly speaking, the router is doing two things. So as soon as a packet arrives, the router looks at the information in the header, uses that to index what's called a forwarding table within the router. And when it gets a match for one of the entries there, it then decides to forward the packet on that particular link. So in this case, the match is for this entry, right? Now, of course, in reality, the IP address is 32 bits long, but here we've just approximated that as a 4-bit field, just to keep this picture simple, right? Now, of course, the forwarding table itself needs to be populated, and that's where routing algorithms come into play. And routing algorithms are executed by multiple routers. So they sort of try to find the best paths from the source to the destination nodes in the network. And based on that, they populate those forwarding tables. And then we looked at this timing diagram. I think these sort of pictures are going to be quite important in this course, where we show you the sequence of messages exchanged between two entities. So this is what a typical timing diagram actually looks like. Let me skip this. Yeah. So this node sends the packet to this packet switch. The packet switch receives this entire packet. It would be doing a lookup in its forwarding table and then decide to send the packet out here. Now, of course, a real packet switch would have multiple links. Now, of course, in this picture, I'm just showing you a simple setup, right? So this process is essentially called store and forward. So the packet switch receives the packet, it kind of stores the packet and then forwards it, right? Now, one important thing to note is in packet switching, the packets travel independently. So the switches here are not sort of remembering that, hey, this node sent a previous packet, I forwarded it here, so the next packet should also be forwarded here. No, the switch doesn't do that. For each packet, the switch will do a lookup in its forwarding table and then decide where to send the packet. So in effect, each packet is treated independently. And as a result, and the fact that the forwarding table itself could change depending on the state of the network, right? So for whatever reasons, if there are certain dynamics in the network and the routing algorithms decide to make some changes in the forwarding table, it may so happen that some of the packets from, say, a source here to a destination here might flow along this path. And then based on certain dynamics in the network, if let's say they're sending 100 packets, some of them may go here, others may go here. After some time, the remaining packets may again go through here, right? So essentially, based on the dynamics, the actual path taken by these packets may actually change over time. Okay. Because remember here, there's no notion of a circuit. There are no reservations being made. So each packet is sort of travels independently. The other point to note is no resources are being reserved. So when a switch forwards a packet, it simply makes use of the entire bandwidth of the outgoing link and sends the packet, right? It's not really reserving anything, right? Now you might wonder, if that's the case, couldn't there be problems? And certainly there can be problems of overloading in the network. But luckily, these switches use, I mean, as you'll see here, switches use the notion of what's called statistical multiplexing, right? So let me explain that through these slides. But before that, there's a question from Jonathan. Is the different paths traveled relevant to us? I'm not sure what you mean by relevant to us, Jonathan. I mean, if you're talking of the end user, no. I mean, from our perspective, so let's say you have an application running, right? So from the application's perspective, it doesn't really matter, right? As long as the data is getting to the other side, the application doesn't care. So for example, right now, when you're watching this Zoom stream, perhaps the first half hour of this stream was sent along one path. I don't know, after that, maybe there are certain changes, the remaining packets go through another path, right? So it shouldn't matter to Zoom, the Zoom client on your machine, as long as it's receiving the packets correctly, right? Okay. So yeah, so let's look at this sort of hypothetical example. So let's imagine we have three sort of source nodes trying to send packets on a single outgoing link, right? And let's say this pictures here show you the traffic that's generated by each of those flows, right? So here, this particular flow generates a small burst of packets here, and then it's silent. This one generates a burst of packets here, then it's silent, and this one generates a burst of packet here, and it's silent, right? And let's imagine that's the capacity of the outgoing link. Now, if we were to use something like circuit switching, though this is not strictly circuit switching, but just sort of we'll abstract over the finer details here. And let's say we wanted to use circuit switching, whereby we want to actually reserve a part of the capacity for each of these flows. Now, if you tried to sort of break up these, the capacity of this link, now imagine the height there is the capacity that maps to this height here, basically. So if you divide this up into three, you'll see that you won't actually be able to fit all of these three flows, because this here is equal to this height. So effectively, there's you won't actually be able to accommodate all three flows here. So if you were to use circuit switching, you could only fit two flows, two out of these on this link, right? Because three wouldn't be able to fit. Now, if we were to use packet switching, however, this is not going to be a problem, because if you look at the bursts of packet, right, if I try to align them, you'll see that these are very nicely aligned, in that here the first flow sends, the second flow sends, and the third flow sends. So they're not actually sending at the same time. So effectively, there'll be no overloading, because you can easily fit this traffic on the outgoing link, right? So this is what we mean by statistical multiplexing. So it's basically relying on the assumption that not all flows will send bursts at precisely the same time, right? And if you think about it, this whole concept is very widely used. For example, if you look at insurance, what do insurance company, why don't they go bankrupt, right? Because Of course, they have to pay out certain claims, but at the same time, they're getting a lot of premium, right, from people who are not filing claims, right? Because the assumption is not everyone not all of their customers are going to file claims at exactly the same time, right? So they're going to keep getting these premium, the payments from the customers regularly, but they're only going to pay out a fraction of those customers, right? So the same idea kind of works here, that not all flows, not all end users on the network are going to be sending data at the same time. Of course, that doesn't mean that on occasion, you might have scenarios where there might be a temporary period where there might be a lot of traffic, right? So for example, if there's a huge storm or a hurricane, right, then a lot of people file claims, right? So the same thing, right? But again, hurricanes or storms do not happen all the time. They only all happen occasionally, right? So again, similar idea here. So on occasions, you might have a scenario like this where the bursts are happening at exactly the same time. And then we do have an overload problem, because if you add up these bursts, then you won't be able to fit them on this outgoing link. So now the question is, what do we do, right? Given that we're using packet switching in the internet, given that this can happen, like, right, for example, if there's some major event that happens in the world and everyone wants to sort of watch the news, right? So there can be occasional periods of time where there's a lot of traffic being generated on the internet. So how does the internet deal with this? So the idea is very simple. So to illustrate that, I'm going to use some slightly different pictures. And in these pictures, this is sort of the pipe abstraction that we'll use, where we'll denote the bandwidth, the transmission rate of a link as the height, the thickness of that link. Time is along the horizontal axis. So effectively, this width is the actual time to transmit the packet. We'll talk a bit more about transmission delays a little later today. So just bear with me for a moment. So imagine you have two incoming links, and traffic from both these links is going out on a single outgoing link. Here we have a packet switch, right? And these blocks here indicate the actual packets as they arrive. So you'll notice initially there's only one packet coming in from at this first instance. So this packet can go through, no problems. Then we have this packet come in, that can go through, this can go through. So effectively, the packets are nicely spaced apart, right? So here in this example, there is no overloading. There's lots of gaps, right? And we don't have a sort of instance of time where multiple packets from both links are arriving at the same time. So this is all okay. This is not an issue. Now contrast that with this scenario where you'll notice here, right? So the first two time slots, if you may, there's a burst, right? A bursty behavior in that we have traffic coming in from both the links, and the packet switch can only forward one of those packets at that instance. So we do have an overload happening here. So now the question is, how do we deal with this overload, right? This is what we refer to as a transient overload, because it's only temporary, right? You'll notice here there's a lot of clearance after that. And this again is not a very rare event in the internet. So the simple way to deal with that is to store the extra packets which cannot be sent in a packet buffer, right? So all routers, all switches normally would have some buffers. So in the first time instant, the switch will only be able to send one of those packets. The other packet will be buffered. In the second time instant, again, it's going to be only able to send one of those packets. So now we have two packets in the buffer, two were sent, but not an issue now. In the third time slot, one of those packets in the buffer can be cleared. And in the fourth time slot, the second packet in the buffer can be cleared. And then we can keep moving forward, right? So having these packet switches do allow us to very easily solve the transient overload problem, right? But then you might say, okay, what if there's persistent overload, right? So what if you have a scenario like this, where you have a constant flow of incoming packets? Well, this is going to be a problem, right? This is something that buffers won't be able to solve because, yeah, you can store the pending packets in the buffer, But if you just have an unending stream of packets coming in like that, this buffer is going to run out, because you can't obviously have an infinite buffer in a practical scenario. And so eventually packets will start getting dropped, right? So yes, if there is persistent overload, we have a problem, and we'll explore how this can be still dealt with a little later when we look at TCP. So just to sort of give you a peek ahead, TCP uses a mechanism called congestion control, where it tries to detect if such situations do occur, and if such situations do occur, it will throttle the sending rate. So it will start reducing the rate at which packets are being pushed out to clear out this buffer and avoid this overload problems. But in any case, we'll come back to that a little later, right? So now just a quick, now that we've looked at packet switching and circuit switching, I think we need to just have a quick look and sort of spend some time on analytically comparing the two, right? So this is a setting as you see here, as you see here in this picture, right? So we have n users. Imagine they're trying to send traffic on a network, and imagine all of these n users want to send packets to the same outgoing link, right? And remember, here we could be either using circuit switching or packet switching. And what we are going to try to contrast is on this particular network, where say we have a 1 megabit link, and we have n users, where each user sends data at 100 kilobits per second when it is active, and each user is roughly active 10% of the time, right? So the question we are trying to answer is how many users can we support on this network given these settings, first in circuit switching and then in packet switching, right? So let's start with circuit switching. Now remember, in circuit switching, we don't care about this, right? Because remember, we said that in circuit switching, we establish a circuit, we keep the circuit alive as long as the user wants to send data, and then we tear it down, right? So in this setting, we are assuming that all end users are sort of alive and on the network. They may not always be sending because they're only active 10% of the time, but they're online, right? So they could send at any time. We just know that on average, over a long period of time, each user is only sending 10% of the time, right? So what that means is, if you're using circuit switching, for each user, you have to set up a circuit, and that circuit has to reserve 100 kilobits. It doesn't matter if the user is active at this time instant or not, right? Because the user is always active, essentially, right? Always online. They may just not be actively sending data, right? So hopefully that helps you figure out that with circuit switching, determining n is fairly straightforward, because if each user needs 100, and if the capacity is 1 mega divided by 100 kilo gives us 10 users, right? So hopefully that's clear enough. If not, to ask me a question on that. But what we'll do is we'll move on to packet switching now, which is a bit more trickier to understand, right? So it turns out that with packet switching, we can actually support up to 35 users, such that the probability that more than 10 of them are active at the same time is very minuscule. So it's as low as 0.0004, right? Now you might wonder, where did I get all these numbers from, right? So I'll come to that in a minute, okay? But just bear with me, because I've got a bunch of slides on that. But the key point here is this. So with packet switching, we need to make sure that the probability that we never, what we are really after is, what's the probability that more than 10 users are active at any given time? Because that's when we are going to have that scenario of overload, right? Now, you might say, okay, what if we are using buffers here, right? So yeah, sure. But in this simplifying, if we want to formulate this whereby we account for buffers, the mathematical problem is going to be intractable. So in this setting, we are assuming the there are no buffers in the packet switch, right? So which means we never want a scenario where there would be more than 10 users actively sending at the same time, right? So that's what we are trying to formulate essentially. But before we get to that, let's look at a question from Zain. Sounds like hardware side of multiplexing takes longer than software side of organizing packets using compute resource. I'm not quite clear on that question. I mean, usually things in hardware always work faster, right, than software, because then you're really dealing with the actual hardware. And if the hardware is designed for that specific purpose, then it should normally work faster. Though I'm not quite clear on the context of that question here. So for example, the routers, if you look at them, routers use specific hardware. So there are ASIC chips that are manufactured with the sole purpose of forwarding packets, right? So of course, your computer here, your basic whatever laptop you're using can also be set up as a router, but your computer is a general purpose computing device, right? So the rate at which it's going to forward packets is going to be much slower than a more specific router, which is designed to forward packets. Of course, a router can't do all the other general purpose computing that your computer does, but it is specifically designed to forward packets faster, right? So in that sense, you can actually do things much faster in hardware, right? I'm not quite sure of the context of your question, but we can discuss that further. Let me just grab a sip of water. Okay, so let's now move back to this formulation and try to work out where do I get these numbers from, right? So to do that, we'll go back to your high school probably, where you have looked at this very basic probability concepts, right? So perhaps you remember this binomial probability distribution. I don't think I have a coin on me, but in any case, if you may remember tossing a coin, right? So something like that, where you're conducting a fixed number of trials, as they're called, and the outcome of each trial is basically, you have two options. The outcome is either false or true. So it's either a heads or a tail. So it's a success or a failure, right? So these are what we refer to as binary random variables, in that the outcome of the trial can only be one of two things, right? A success or a failure. And let's say the probability of success is P and the probability of failure is 1 minus P, right? So if you consider a coin, P, unless it's a loaded coin, the P will be half, right? So the probability of heads is half, the probability of tails is half, right? And of course, the probability remains constant for each trial. It doesn't change, right? So what's the probability that you get a sequence where you have 3 heads, right? If I toss a coin 5 times, what's the probability that I'll exactly get 3 heads, right, out of that? So one way to get 3 heads is as shown here. So you get 3 heads and then two tails. Another way would be something like that. And of course, the probability of this sequence is half times half times half, basically half times half raised to the power 5. This sequence would also be half to the power 5. So now really the question is, how many such unique combinations would generate 3 heads, right? So if you work through that, you'll see that you can actually have 10 possible such arrangements. And you might have seen this expression before, which allows us to sort of compute how many combinations you can have of gathering 3 elements out of 5 total elements, right? 5C3 as it's often called. And you may remember that this is equivalent to 5 factorial divided by 3 factorial times 5 minus 3, which is 2 factorial. So there are 10 possible arrangements in which you can arrange this. And so the probability that we get 3 heads and 2 tails would be 10 times or essentially 5c3 times half raised to 5, right? So in a more general setting, this is what you would get, right? So if you're running n trials where the outcome of each trial is essentially a yes or a no, where the probability of yes is p, the probability of no is 1 minus p, then in general, the probability that you get x successes would be ncx, this part here, p to the power x, 1 minus p to the power n minus x, right? Hopefully you do remember this from whenever you learned probability theory, right? So now you can actually use this probability theory to solve that particular problem, right? So remember earlier I said that we are trying to figure out what would be a value of n such that the probability of the number of active users that's greater than 10 should be ideally 0, right? Ideally, we never want more than 10 users to be active at exactly the same time. Now, if you were to, if you remember again, the probability of something greater than 10 like that would be 1 minus the probability that the number of active users are 10 minus number of active users are 9, 8, so on and so forth, until the number of active users are 0, right? So what we should be really doing is sort of formulating this expression where each of this would be something like that, right? And essentially this would be n, just forget the 35 for a minute, right? So Cn times, sorry, nc10 times 0.1 raised to the power of 10, because remember each user is active 10% of the time. So P here is 10% and 1 minus P is 0.9, right? So ideally we want to sort of generate this expression, and we should be trying to figure out n such that this equates to 0. Now the problem with setting up a mathematical formulation where if you say it's equal to 0 is you won't be able to solve that, because you can't really solve an expression like that where the result is a 0. So that's why we can't use a 0 and we need to use a very small value. So in this case, I've chosen, again, just randomly this small value. You could choose a slightly different value if you wanted to, and sort of try out. It's very likely you'll get a very similar answer though in that case. And then you write up this sort of long form expression and you try to figure out what would be the value of n that gets us this probability. And in this particular example, it turns out that n equates to 35, right? If you were to relax the probability a little bit, in other words, if you chose a slightly higher value, say, I don't know, I don't know, I'm just making it up, something like 0.01, you would very likely get a larger n, essentially, right? So it really depends on the choice of this here. Essentially, what's the chance? What are you comfortable with as a network designer, right? What do you think is a point where you're comfortable with? So you can certainly support more users, but then the likelihood that more than 10 of them are going to be active will also be higher, right? Which means your network might get overloaded, right? So this is essentially a question that when you're designing a network, you would set up a formulation like this. Of course, probably you won't do this by hand. You would have computer programs to do that. But using simple heuristics like that, you can sort of get a feel for how to provision your network, right? So this is not just a question of applying math for the sake of it. There is actually practical use of this math. Now, mind you, when it comes to an exam question, I can't really ask you something complicated like that. You can't actually feasibly solve this on pen and paper. You would very likely need to write a program to solve this whole mathematical expression. So certainly I won't give you very complex problems like this, but you can expect some other kind of problems based around taking this concept of probability theory and applying it in the context of packet switching, right? And you'll actually find some examples in the homework questions. Okay, so some last words. So generally, the bottom line is with packet switching, you can typically support a much greater number of users than with circuit switching, simply because packet switching exploits the idea of statistical multiplexing. So is packet switching always better? Well, it's generally better if the traffic pattern is bursty, right? Which is indeed the case. I mean, if you think of end users and if you look at your profile itself, how are you using the internet? What is the traffic you're generating, right? So you'll see that it's actually bursty. So right now, for example, you're watching this video feed. So certainly there's this constant, fairly bandwidth intensive application you're running, but maybe after this lecture, you stop, you're just browsing the web, you're replying to emails. So again, at that point, your traffic drops. Then suddenly you might go and watch a YouTube video. Later, you might listen to some music. So essentially, the traffic we generate is typically very bursty, right? So that's where, that's why it's quite amenable to packet switching, essentially. On certain occasions, though, in the internet, you will see some congestion happening, right? So there will be occasions where, particularly say peak durations, for example, typically at late at night, there's usually less traffic being generated than say at 9 a.m. and things like that, right? So on occasion, you will certainly see congestion where there will be scenarios where we'll get those transient bursts. You might have a lot of packet queues being built up, and occasionally you'll also have packets getting lost due to the buffers filling up. So we do need to account for that, and you'll see little later when we look at TCP, how it actually deals with some of these issues using a mechanism called congestion control. So I think we'll leave it at that. There is a question here. Joseph is asking, there is a great computation effort to compute probability. Yeah, exactly. So I mean, this was just to sort of give you a sense for how to do this, right? So this is just to show you that simple math like this can actually be applied in a real network setting. I mean, strictly speaking, it's not that difficult, Joseph. You could write up a simple program. I mean, of course, doing it by hand is certainly difficult, but writing up a simple program, it will just be a few lines of code. Right? So from that perspective, it's not too hard. Yes, I do agree. I mean, as I already said, you won't be asked an exam question like this, but there are variants of this where you could do the probability calculation just in your head, which could be asked. So you can find some of those sample questions in the homework set. Okay, so let's pause for a minute and ask you to provide me some answers. So if you could kindly go to pollev.com/Salil and answer this question, please. Okay, let's have a look. Yeah, that is correct. Well done, everyone. The answer, most of you, I guess, the answer would be packet switching. In circuit switching, the resources are sort of provisioned right from the start, right? So I know perhaps the wording is could have been a bit better, but what I mean here by on demand is you're not making reservations in advance, right? So with packet switching, as we saw, when a packet arrives, the switch will forward it if it can. If not, it's just going to store it in a buffer, right? So that's what we mean by on demand. Whereas in circuit switching, we actually need to explicitly make advanced reservations, hold those reservations till we are sure that the user is no longer going to be sending data anymore, right? So the correct answer would be packet switching. think there's another one. So let's look at that. Oh, I need to activate it, I think. This again is a bit weird in that I've said in circuit switching, we are sending packets, but hopefully you get the gist, right? Could think of it as two chunks of data effectively. I mean, you could. Okay, let's see what you've responded. Yeah, this would be in. So remember in circuit switching, oh, sorry. This is incorrect. My answer is incorrect. Sorry. The answer would be is the same, right? So when you're talking of circuit switching, remember we said that we first reserve the circuit and then all the traffic will follow that same path unless explicitly there's one of the links breaks and then we have to reset the circuit, right? So that, I mean, in the question doesn't talk about resetting circuits or anything like that. So the assumption is that you establish the circuit, all traffic that's being sent from device A to device B follows that same path. So all data chunks being exchanged between those two endpoints have to follow that same path. So the answer would be is the same in this case. Is there another one? Oh no, this will come to later. So let's move back. Yeah, so the correct answer would be A. By the way, I know some of you may ask, at the end of the week, I'll add the answers and re-upload the slides just so that when you're sort of going through the slides later, you know what the answers are, right? So you don't have to go back to the video just to look for the answer. Okay, so let's now move forward. So remember here we were talking of the core of the internet. We looked at what are the underlying technologies that could be used to set up the core. So we looked at packet switching, we looked at circuit switching. We saw why packet switching is better and that's what is currently used. Now we are zooming out a little bit and trying to understand how the core of the internet is actually structured, or in general, how is the internet itself structured, right? Remember earlier we talked about the internet being a network of networks. So that's what we'll be looking at. So there's a question here. I thought circuit switching reserves dedicated paths for each packet. No, Toshi, that would be even worse, right? I mean, if you think about reserving a packet for path for each packet, in circuit switching, what we do is for all communication between two endpoints, we reserve a path and keep using that, right? So it's for one connection effectively. If you do it for each packet, then it's going to be even worse, right? I mean, you send a packet, you reserve a connection, you send one chunk of data, then you close. Then for the next packet, you would again do that. So that would be even worse, right? Yeah. Okay, so yeah, so here we are talking of, we've already looked at the access networks, right? And we saw that access, there are different settings. Essentially, you can have a residential access network, you can have an enterprise network, and then of course, we have mobile and wireless access networks. But the access networks can't just stay isolated, right? We need to connect these access networks together. Otherwise, we are just going to have these islands of networks which cannot talk to each other, right? So this means that we need some other networks that are interconnecting these access ISPs. And this whole, if you want to actually map the internet, it will quite look very complex, right? Because there's I mean, remember, we are talking of a global network, right? And there are what, 190 countries or something like that in the world, over 9 billion people. So really, this is a humongous, complex network of networks, and a lot of the evolution is driven by policies, in fact. So a lot of these decisions may not necessarily be technologically the best, because there are various national policies and economics to consider, right? So we'll kind of abstract over some of these, because these are clearly not of interest to us in this course. And we'll really be just sort of looking at this in a fairly high level abstract sense, right? So imagine you have these millions of access ISPs. Now, how would you connect this together? So a strawman approach could be, you could say, hey, let's take each access network, connect it to every access network around the world. Wow, that might sound fantastic, but obviously this doesn't scale, because that would mean you would need order of n square connections, where n itself is in the order of millions, right? So obviously this won't work in practice. Okay, so then what do we do? So could we have like a single global ISP that connects all the other access networks? Sure, on paper, yes. But again, in practice, what would a global ISP look like? Who would run that global ISP, right? And why should there only be one? Wouldn't it make sense then to have some sort of competition? So clearly there's a sort of, again, going back to this whole capitalist society that we live in, of course, there would be a need then to have multiple such global ISPs who are interconnecting all these access networks together. And then, of course, again, you can't just have isolated global ISPs. You need to interconnect them to each other. And this is where we have what are essentially referred to as internet exchange points, which are essentially huge buildings with a huge number of routers and cables running through them, where you interconnect all these global ISPs, right? Remember, here we are talking of connections that can carry, like, I don't know, terabits, even higher. What is after terabits? I forget. Zetabits, something like that. That we are talking of that scale of data, really, right? And of course, you might also have ISPs directly having what are called peering agreements with each other. So essentially, they sort of get into agreements and agree to forward each other's traffic. There might be some monetary exchange happening as well. So yeah, there's all this sort of complex mechanisms in place. And then, of course, below that, you might also have regional ISPs, right? Particularly in large countries where you're spanning out, like even in Australia, where even though the population may not be large, the actual physical land is fairly extensive, right? So there would be a need to have even regional ISPs below the global ISPs. And finally, very recently, in the past 10, 15 years, we have all these content providers creating their own networks, right? So Google, Microsoft, Amazon, Netflix, you name it, right? So they are trying to push their content as close as possible to us. Their sole purpose is to reduce the latency, right? So the whole purpose is for us end users to be able to enjoy the content as quickly as we can. And the way they try to do that is by actually immersing their servers into everywhere around the globe, essentially, right? So they're sort of overlaying their content provider networks on top of that. So already, even with this simple abstraction, you see that the internet is starting to look very complex, right? So if you were to really draw this in some simplified manner, it would look something like that, right? So you have these top tier ISPs, which are referred to as tier 1 ISPs, which have national and international coverage. You have content providers like Google. We have regional ISPs, and then we have access ISPs, right? And then we have these exchange points. Essentially, these could be thought of as like important interconnections on the internet highway. where all these networks sort of interface with each other. And of course, these are all sort of, so for example, a regional ISP is a customer of a tier 1 ISP, and access ISP is a customer of a regional ISP, and so on and so forth. So there are these hierarchies in terms of who's paying whom, and so on and so forth, right? So yeah, it's a fairly complex setting. So this picture, for example, is showing you a tier 1 ISP network map for Sprint, which is one of the tier 1 ISPs in the US. And as you see, it spans across the entire North America, in fact. And this is typically what's referred to as a point of presence. So this is where two ISPs may directly peer with each other, right? And again, each of these, even though we refer to them as dots here, these are actually, there's a lot of infrastructure put in there. There's like several hundreds of routers interfacing with each other. Now, if you look at the UNSW, right? So you might wonder, okay, how is the UNSW network connected? So in fact, most, or I think all universities in Australia, the ISP for us is an organization called AARNet. So that's the Australia's academic and research network. So this picture I've got from their actual website. So this shows the network that they've actually deployed. And you see that they have a fair amount of global coverage. And of course, then they have agreements with some of the other providers in other parts of the globe, right? So I think the yellow colors, I think, typically indicate the partner networks. So these are not actually deployed by ARNet. So that's the international network. But I think the ones that are not in orange, or whatever this color is, yellow, are the ones that are actually deployed by ARNet, right? And in fact, I'll walk you through this map a little later when I'll run some traceroute examples here in the lecture later. This is also another interesting thing to look at. So in fact, I might have that link open here. Where's that? Yeah, so this shows you, so you might wonder how the network actually looks like, right? When we're talking of global coverage. So given that there's a lot of oceans around us, so the actual traffic is carried in cables that are deployed on the ocean floor. So for example, here we are, right? So obviously there's a massive ocean between separating us and the United States. So there's these deep sea cables that run all across the ocean floor from Australia all the way to the US, right? They do emerge up here in Hawaii, as you see here. And then they run further into the US. So similarly across the Pacific here, from the US to Asia, across the US to Europe, everywhere really, right? So these are actually carrying humongous amount of traffic. So for example, let's look at this one. So this one is actually deployed by Telstra, as you see here. That's the length of the cable, over 9,000 kilometers. Does it actually tell us how much traffic it's carrying? Maybe not. In any case, you can have a look at this later, right? It's just amazing to look at some of this, right? The other thing I might show you is, so this is a IXP. So I remember in the picture earlier, I showed you these internet exchange points where multiple networks actually peer with each other. So this is an IXP located here in Sydney, and you'll see that a lot of networks are actually interfacing there, right? So you have, of course, ARNet, which I just showed you, the university network, Akamai, which is a major content provider, Alibaba, Amazon, AT&T. I'm sure you, Cashfly, which is again a Cloudflare, another content provider. I'm sure you'll find Netflix as well, Facebook. IINet, again, a provider. Limelight, which is also a content provider. Microsoft. So pretty much, yeah, Netflix, there you go, right? So any content provider in the world, as you see, there's so many networks interfaced here at this IXP, right? So it's like a very important exchange point, essentially, where all these various networks are interfaced. Right? Yeah, this I already showed you, the ARNet network. Yeah. And again, you might want to also have a look at Google's network itself. So I'll leave it for you to look at, but essentially Google, as you may expect, has a massive deployment of networks. Of course, they have their own data centers, which are again massive, where they host a lot of data, but then they have these points of presence where they interconnect with various networks, and they also deploy their own caches. So the fact that Google, of course, owns YouTube, and YouTube, of course, serves a lot of videos. So what they do is all the popular videos, they actually deploy in caches, which are directly embedded into various ISPs. So a lot of ISPs here in Australia would actually be hosting Google servers within their network, which allows us to watch YouTube videos fairly quickly, right? So rather than going to overseas servers, the videos can be sourced locally from where we are. Okay, so I think it was a bit of a diversion, but hopefully still useful for you to see. Now, this might be a good point to actually take a break. We're just about 1 hour into the lecture. So let's pause for a minute, take a 5-minute break. I'll pause the recording, and then we can come back and start looking at some performance issues. Right? There's a question I'll take before I go to break. So would points, Tim is asking, so would points of presence be their own infrastructure while caches are hosted on someone else's infrastructure? That's a good question. So I think point of presence, I mean, it's hard to generalize there because there could be various models for that. So a point of presence is typically where one ISP is interfacing with another one, right? So this could very simply just be one simple router that's installed, or it could be more extensive infrastructure, right? So it really depends. It's hard. It's not like there's a written rule that says, okay, a point of presence exactly has to look like that, right? So it's a bit of a fuzzy term, if you may. And you'll see various instantiations of that, right? But normally, say when we are talking of content providers like Netflix, I think they actually provide the infrastructure. So they are actually providing physical infrastructure to the ISP, because think about it, right? Why would the ISP, let's say TPG, why would they invest their own money into hosting some infrastructure when content providers like Netflix will gladly give it to them, right? So again, there's some economic aspects also involved here. Matt is saying points of presence are converged in meet rooms and data centers. Yeah. Okay. Yeah. Thanks, Matt. I don't quite get that sentence as well, frankly speaking. But we can talk about that. There's a question here: is the link to the Ed discussion forum supposed to be working? So Yundong, you need to first join the forum. Without that, you won't get access. So if you go to here, so first join it. And once you join it, you should be able to. It does work, I think. I'm not sure why. So that's what I get. You have to click it a few times before it let me through. I'm not sure why that is happening. yeah, maybe have a look at it again and let's see what you get later. In any case, let's take a pause here. I'll pause the recording and then we get back in about 5 minutes. Hey everyone, I'm back. I forgot to show you my bad meme. So you can have a bit of a laugh and then you can get back to where we were. Okay, so let's get back to talking about the performance issues. So we'll be looking at mainly delay and throughput. There's not really a lot to talk about packet loss as such. What's happened? Okay, right. So we briefly talked about the fact that in packet switching, you might have occasions where you might have transient overload. And to deal with that, packet switches will maintain some buffers. So during times when there's a lot more traffic coming in than what the switch can actually forward, the packets will temporarily be stored in the buffer, hoping that in the future there'll be instances where there'll be an opportunity for those packets to be sent out, right? So that's and the side effect of that obviously is that the packets that get stored in the buffers will have to wait till they get an opportunity to be sent out, right? An issue there is if the queue is very large, then packets that are at the tail of that queue will have to wait a lot longer than say packets at the head of the queue, right? So having queues is great, but then if the queues are constantly full, then also we have an issue, right? Because those packets are going to be delayed. And remember, in the end, we've got applications running on end hosts that are trying to communicate. So those delays will start could start impacting the applications that are running, right? And again, we'll see some differences later, like applications like email and applications like that are not very synchronous may actually tolerate such delays. But then other applications like say when you're watching a movie or when you're participating in a live conference, say a video conference or a video call, may be impacted a lot more, right? But in any case, we'll look at that a little later. So yeah, so if you look at what's actually happening within a packet switch, so when a packet is being transmitted, we refer to that particular delay as the transmission delay, which we'll look at. Packets that get stored in the buffer, they experience queuing delays till they can move forward to the head of the queue and be transmitted. Of course, when the packet queue gets full, so imagine all of this turns green, then any further packets coming in cannot be accommodated and those do get lost, right? And then of course, the issue becomes what happens when packets get lost, and we'll look at that a little later. So let's first focus on the actual delays and the various types of delays at an individual packet switch. So didn't you say packets have a TTL of 1 millisecond? So wouldn't losses occur more often than delays? I don't remember saying TTL of 1 millisecond, Zain. TTLs would be a little larger than that. Otherwise, that would obviously be a problem. Maybe that was just an example in one of the slides. Practical values of TTL, we'll look at that a little later, but they certainly would need to be more than a millisecond, because the end-to-end, typical end-to-end delays will be much larger than a millisecond, right? Okay, so if you look at the delays that occur at an individual packet switch, there are actually 4 delays we need to look at. And of course, the summation of all of those delays would give you the total delay at each switch, or what we refer to as each node here, basically. So we have first what's called the processing delay. So when a packet arrives, the switch first does a number of things. It checks if there are certain errors in the bits using mechanisms like checksum, which we'll look at later. It does a lookup in the forwarding table to figure out where to send the packet to. Now, if you add up all those delays, those are typically very minimal, right? So even though it's saying here milliseconds, they can be as low as nanoseconds in some of the core routers, right? So we normally disregard this delay. We assume this is negligible, right? Unless explicitly told. Right? So the processing delay is typically low. The next is the queuing delay. So this is the time that the so imagine, I mean, if you look at the exact sequence, right, at least here in this abstract sense, a packet arrives. The first thing that happens is the packet gets processed. Then once we know where the packet is headed to, because remember, each switch will have multiple links. So the next thing the route switch needs to do is send this packet out on that outgoing link. Now, of course, there may be other packets waiting to be sent on that outgoing link in a buffer. So in that instance, if that is the case, then the packet gets queued up. It gets put at the end of the queue, let's just say for simplicity. And then it has to wait for the queue to clear out before it can be sent out, right? So this time that a packet has to wait till it can be actually transmitted is called the queuing delay. Now, the queuing delay can be extremely variable because it depends on the level of congestion at that router. You might have an occasion where there's no packets waiting in the queue, in which case the queuing delay would be 0. In other instances, you might have the queue being almost full, and then the packet has to wait for several, I don't know, milliseconds, several seconds even to get out, right? So the queuing delay is extremely variable, and we'll look at that a little more in just a couple of minutes. The next thing is the transmission of the actual packet, right? So imagine the packet now gets to the head of the queue and now it should be transmitted. So the transmission delay is the time to actually push out the packet onto the link, right? So that process of actually putting the packet out on the link is referred to as transmission delay. So that depends on the size of the packet, the length, and the bandwidth, or the transmission rate, as we call it interchangeably. So this is basically L by R, right? L is in bits, R is in bits per second, right? So this that gives you the transmission delay effectively. Now, once the packet is out on the link, it needs to physically move along the link, right? Doesn't matter if the link is wired or wireless, the packet has to propagate essentially through the link, through the medium, and that is referred to as the propagation delay. Now, the propagation delay will depend on the length of the link, either the physical or the free space, essentially, the distance between the two nodes, and this propagation speed. So the propagation speed is the speed at which bits can actually move on the physical link. Now, in most instances, this is very close to the speed of light. As you see, if you remember, the speed of light is about 3 times 10 to the order 8. So the propagation speed is roughly either 2 to 3 in that range, basically, right? And so the propagation delay will largely depend on the distance, because this is typically always close to that. So if these two nodes are far apart, then there will be substantial propagation delay, right? So like the submarine cables I showed you. So for example, the time for a packet to propagate, say from Sydney, one end of that cable to say Hawaii, it would be fairly large, right? Because it has to move through several kilometers, as opposed to say a packet going from my computer here to my router at the back there, right? Which is just maybe 2-3 meters apart, right? And do remember, these are very different. Sometimes people do get confused about these differences. So again, remember the transmission rate is the rate at which you're pushing packets out. The propagation delay is the rate at which, once the packet is out, it has to actually move on the link, right? So a good analogy, which is also in your book, and I'll quickly go through this, you can read a bit more about this later, is this caravan analogy, right? So imagine we have this setting where we have a caravan of 10 cars, and imagine there's toll booths on a highway, and imagine there's no other traffic on the highway except this caravan, right? So these, imagine the cars are being driven, essentially propagating at 100 kilometers an hour. Imagine the distance between the toll booths are 100 kilometers, and imagine the toll booth takes 12 seconds to service a car, right? So you could imagine that to be the transmission time of a bit. So a car is effectively a bit. The caravan is the packet, which is made up of 10 bits in this case, right? So the question here is, okay, imagine we have this caravan lined up here. Now, how long does it take for this caravan to move from here to here, right? And line up there. So effectively, that would be the time to push the entire caravan through the toll booth. Now, in this instance, there's no processing delay, there's no queuing, because there's only this one caravan that's being transmitted. So the time to push the entire caravan would be 12 seconds times 10, right? Because 12 seconds is the time to push out one bit. We have 10 bits. So 12 times 10 is 120 seconds. And then once that caravan is out here, then it must propagate from this toll booth to the second one. And since the distance between those two toll booths is 100, and given that the propagation speed is 100 kilometers per hour, it would take 1 hour for this whole caravan to propagate from one toll booth to the next. So if you add those two up, 1 hour plus 2 minutes here, that would give us 62 minutes, right? So hopefully that's clear. Now let's change the setting a little bit. And now imagine the cars are propagating at a very high speed. I know this is perhaps physically impossible, but let's just imagine that cars can propagate at 1,000 kilometers an hour, right? And let's imagine the toll booth is very slow. It's taking 1 minute instead of 12 seconds to service a car, right? So in this setting, it's asking you whether cars will, from this, like some of the leading cars here, could they actually arrive at this second toll booth while the tailing cars are still being processed at the first booth, right? So imagine you have a scenario where the cars sort of extend like a snake across this whole road, where some part of the caravan is already reached the second toll booth while the tail is still here, right? And that can actually happen, because if you do the math now in this case, the cars are propagating at 1,000 kilometers. So I think 100 by 1,000 kilometers, I think it comes to about 6 minutes to propagate from one end, from one toll booth to the other. So once a car has been pushed out, it will take 6 minutes for it to get to the other toll booth, right? And the time to push out a car is what? Is 1 minute, right? As we know. So the transmission rate is one car per minute, right? So imagine you have this caravan lined up. So you push out this first car, it takes 1 minute, and then that car takes 6 more minutes to get to the other side. So in 7 minutes, the first car is already lined up here. I know I'm bad at drawing, but imagine that's what's happened, right? So by minute 7, the first car is already here, right? And since it's taking 1 minute to push out each car, and since there are 10 cars, you'll see that by minute 7, the first 7 cars have left, but the remaining 3 cars are still lined up here, right? So effectively you have a scenario where the tail of the packet is still at the previous packet switch, whereas the head of the packet has already reached the other side, You might wonder, how is this possible? Is that even making sense? So in fact, there is this nice applet that I've linked from the website. In fact, it's on the slides as well. So you can actually play around with some of these numbers to see what happens, right? So we have this setting where we have a 10-kilometer cable between the sender and the receiver. The transmission rate is about 100 megabits. The size of the packet is 1000 bytes, and the propagation speed is very close to the speed of light. So let's see what happens. So you'll see that this goes very quickly, right? So packet is pushed out, and maybe we'll slow it down a little bit. There you go, right? So the propagation delay is that much. The transmission delay is about 0.02 here in this case, right? Now what you can do is you can also make the propagation delay very long. So imagine this is now a undersea cable or something like that, right? 1000 kilometers. So you'll see it takes quite some time for the packet to actually propagate, right? Simply because of the physical distance between the two endpoints, right? So, and then the transmission time is very small compared to the propagation delay, right? You could also have a setting like that where, oh no, sorry. Yeah, something like this where, so this is that what I was referring to in that next slide, where the head of the packet has already reached the receiver while the tail is still being transmitted, right? This is because the transmission delay is fairly large compared to the propagation delay, right? So something like that. Again, so you see the head of the packet has already reached the receiver while the tail is still being pushed out, right? Certainly play around with this to get a feel for the differences, right? But just make sure you understand the key difference between propagation delay and transmission delay. Right? So if there are any questions to ask, I'll just pause here for 1 second. Okay, no questions so far. So let's move on now to queuing delay, right? So this is a entirely different beast because queuing really depends on the level of congestion in the network, right? So, and in fact, there's a lot of math underlying queuing delays. So there's this whole field of queuing theory. In fact, I remember when I was doing my PhD, I did a whole course on queuing theory. It's a fairly fundamental concept. I mean, it's important not just to networks, but really anywhere, right? Of course, now we won't have the time to go into all the math there, all the theory, but I'll just give you a quick flavor of some of the intricacies underlying queuing delays. So we'll use this simple abstraction here. So we'll imagine there's a packet switch. The outgoing transmission rate here is R bits per second. We'll assume all packets arriving are going out on this outgoing link. We'll assume all packets are of the same size. Just to keep things simple, we'll assume packets arrive at a rate of A packets per second, right? So A times L is effectively the total incoming traffic at the router, at the switch, and the outgoing traffic is R bits, right, every second. So what if the total incoming traffic is greater than the outgoing traffic? So that's where we start to have a problem, because that means the queue will constantly keep building, right? Because you just have too much traffic coming in than what the router can service. So the queues will start building up, and eventually the queue will get full with time and packets will start getting dropped. So this ratio, effectively AL by R, is an important one, particularly for a network administrator, a network designer, because this is what's referred to as the intensity of traffic, AL by R. And we want this ratio to be much lower than 1. Because if this ratio becomes equal to or greater than 1, then we have a problem, because then we have a scenario where the queues will keep building up, right? So as a network designer, as a network administrator, you want to operate at the lower end of this range of AL by R obviously goes from 0 to 1. So we want to be not very close to 1 effectively, right? Now let me show you two sort of artificial or unrealistic scenarios, I would say, and then we'll look at what how queuing delays actually look like more realistically, right? So in this first scenario, the way I've set this up is I'm saying that the packets are arriving uniformly, so they are arriving nicely spaced apart. So a packet arrives, and then there's a gap, and the next packet arrives, and then there's a gap, and this gap is fixed effectively, right? So this gap, the time gap between packets is effectively fixed, and that time gap is exactly equal to L by R seconds, right? So packets are arriving uniformly, periodically, separated by L by R seconds. Now, of course, we know that the bandwidth of this link is R. So the time to push out a packet, the time to transmit a packet is also going to be L by R. So in this artificial scenario, you'll see that a packet comes in, it gets pushed out, and just as the packet has left, another packet comes in, it gets pushed out, right? So effectively, you'll see that the queuing delay is 0 in this case, right? Just because the packets are arriving very nicely spaced apart, and they're separated exactly by the time which with this switch takes to push out one of those packets, right? Now, despite that, you'll see that the arrival rate here, if you do the math, it's actually going to be, the traffic intensity is actually going to be 1, because the arrival rate is effectively R by L. This transmission rate is L by R. So if you do the math, you'll see that the traffic intensity is actually very high. It's the maximum possible, effectively 1. But despite that, the queuing delay is 0, right? So this is clearly an artificial scenario, because in reality, packets will never arrive very nicely spaced apart like that, right? Now, in contrast, imagine a setting where packets are always arriving as a burst, right? So imagine that n packets arrive together, essentially back to back, right? And they arrive every ln by r seconds. So you have a scenario like this, or maybe, yep. So that's one burst of packets, let's just say. Then there's a gap, and there's another burst of packets, right? So something like that is happening, right? And this burst is always n, and the bursts are spaced apart by that time, right? So in this case, again, if you do all the math here, you'll see the arrival rate is L by R, the traffic intensity is also 1, right? However, the delays here would be very different, the queuing delays, right? Because you have this burst of packets arriving. Now, initially, of course, the first packet can go through without any delay. So the queuing delay for the first packet is 0, but then the second packet has to wait for the first packet to go out. So it has to wait by L by R. The third packet has to wait for the first 2 packets to go out. So the queuing delay would be 2L by R, and so on. So the nth packet would have to wait for the other n-1 packets to go out. And so if you do all the math here, you'll see the average queuing delay will be like that. Obviously, the packets at the back end of this burst will have to wait longer than those at the front, right? So we have basically 2 scenarios. One scenario where we have this burst of packets and where we see there is substantial queuing, whereas we have another scenario where again, the intensity is the same, but there's 0 queuing. So now the question is, what is more realistic, right? What do we actually see in real networks? Do we see this? Do we see this? Well, the answer is there's been a lot of analysis of how packet arrivals and so on in real networks. And what researchers have said is the best approximation really is to assume that packets arrive at random. So they neither arrive like that consistently, nor do they arrive like that. So you might of course get occasional bursts, and you might of course get occasional instances where packet arrive periodically. But a good approximation is to just assume packets arrive randomly, right? And in that setting, if we do assume packets arrive randomly, then the queuing delay can be mapped out like this. Now, again, you might ask why? Well, there's some math associated with that, which we won't have the time and capacity to get into. So you just sort of take my word for it for the moment, where we'll say that initially, when the traffic intensity is very low, the queuing delays are very low. As the intensity starts building up, the queuing delay starts to ramp up exponentially, because now here, somewhere in the middle, we have more instances of these bursts happening. And as we've seen with bursts, the queuing delay starts to increase because the packets at the back of the burst have to wait longer. But then once we start approaching 1, you'll see that the queuing delay starts getting appreciably larger. So here we are talking of seconds of delays, right? It could even go as high as minutes if you really push the intensity close to 1, right? So really, when you're operating a network, you ideally never want to get into this region, right? Where the delays are shooting up exponentially higher, right? So as long as you're somewhere in the middle, you're okay. Once you start getting here, you're in trouble, because then there's a lot of queuing happening. Potentially, you can have instances where packets start getting dropped, and then we'll have all sorts of problems in the network, right? I think we'll leave it at that. There's again a nice applet you can play around with. I might have it open. Unfortunately, this is not very configurable. There's only a few options you can select, but you can sort of play around with this and observe what happens. You'll have to keep this running for a while, unfortunately, for the queues to build up. But again, that's something you could play around in your own time. Right? So effectively, if you're mapping out all the 4 end-to-end delays, this is again a timing diagram. I've changed it a bit here. The time is actually on the horizontal axis. In most of my previous pictures, I've shown you time is on the vertical axis. But effectively, if you map this, right, so there's the time to actually push the packet out. So that's the transmission delay. So, oh no, sorry, this is the propagation delay, sorry. So the time to push the packet out is this, L by R. Once the packet is out, it needs to propagate. So that's D1 by S, the propagation delay. In this particular instance, this router has no other packets in the queue, so there's no real queuing happening. There's a small amount of processing delay that's accounted for here. Then the packet gets pushed out onto the second link. So that would be L by R2. The propagation delay would be D2 by S, L by R3 when it gets pushed out here, and D3 by S. Now, I think in this particular picture, R1 is equal to R2 is equal to R3. So you'll see these bars are all of the same size, right? But you might want to consider scenarios where that may be different. You might also have occasional instances where packet gets queued behind other packets, in which case there would be some extra delay accounting for some of the queuing, right? So this is what you might want to have a look at. And then imagine if you're sending back-to-back packets, so then the second packet might be coming right behind, right? So imagine this client is sending another packet here, back-to-back. So something like that. And then this second switch also sends that packet back to back, and so on and so forth, right? So you could have a go at this. I mean, just take a piece of paper and sort of map out some of these delays. So there's a question from Matt: is there any delay in the client sending successive packets? Yeah, exactly, Max. So that's what I was trying to draw here, right? So when you're talking of back-to-back packets, so remember that some of this can be happening in parallel, right? So when the second packet is being sent here, the router might already be sending the first packet, right? Because the router here doesn't have to wait for all packets to come in. When it gets the first packet, it can start sending it. So there's, as you see here, that can happen back to back in a sense. And then the first packet could be sent here, the second packet could be here, the third packet could be here, and so on and so forth. So they kind of follow each other effectively. So hopefully that answers your question. Okay, we are still okay on time. So let's now look at some real examples of delays, right? So this is something you'll be doing in your first lab next week. So there's a program called traceroute, which allows us to actually measure delays along the entire path from, say, a source host to a destination host. So the way traceroute works is fairly simple. It sends out 3 probes to every router along the path. So here you notice it's sending out 3 probes to the first router. It will start a timer, send the probe, and wait for the response to come back, stop the timer. So it measures effectively the round trip time between this host to the first hop router, and it does it 3 times. Then it will move to the next router, next router, next router, and so on and so forth, right? Till it actually gets to the destination. So the output would look something like that, right? So you notice there are 3 measurements. In fact, let me do a live trace route as well. Where should we trace route to? So I studied at a university called Drexel in the US. So let me do that. That's based in Philadelphia. Hopefully you can see this. It's not too tiny. Maybe I can increase the font a bit. Right. So you see here, these are the first hop router, second hop router, so on and so forth. So I'm actually on a VPN right now. So that's why it's showing the CSE network here, not my home network. Okay, so what are our observations here? So firstly, let's see here. In fact, you'll see some of these routers are being mapped to certain names, and that already starts telling you a bit about how the packet is progressing. So first thing you'll notice is this has kind of halted. This is basically just stalled. You're not getting any outputs, right? So you might wonder why that's happening. Well, a lot of network designers will disable traceroute responses. So you'll notice by hop 25, we have already reached the Drexel network, right? And now the packets are starting to enter the Drexel internal network itself. And the Drexel network administrators have actually disabled these responses because they do not want to reveal the entire structure of their network to external, to some random person in Australia who's trying to trace route their network, right? So you will see this behavior a lot. Once the packet reaches close to the destination, you just start getting this unending responses because this machine keeps sending trace route messages, but there's no response coming back, right? So it kind of keeps in sort of going in an unending loop. Eventually it's going to quit, but it's going to take a lot of time for that. So let me just kill this for now, right? So this is one observation that you'll see, that in some instances you just don't get any responses, and that's because those traceroute. So if you look here, some of these routers here, as we get close to the destination, they're simply not responding back. So you keep sending probes, they're not responding, right? Oops. The second observation I can make is, if you start looking at these delays, you'll notice here the delay is 71 and 2. So the delay has increased by almost 70 milliseconds. Another thing you'll notice, the delay from here to here has increased by another 100 milliseconds. So what does this mean, right? So typically, again, not always, but typically this is suggesting this hop is very likely an undersea cable, right? So it's crossing across the Pacific Ocean, yeah, as Tim has already pointed out, right? In fact, if you look at the name, it's suggesting this hop is in Guam, right? Guam is a small island in the Pacific. And then this next hop is to the internet to network. So just like we have AARNet here in Australia, there's another network called Internet 2 in the US, which provides the backbone, which serves as a backbone to a lot of universities in the US. So in fact, this has now reached the US. All of these hops are in US. In fact, you can do a bit of detective work and figure out that, I mean, this is Kansas, this is probably Chicago, that's perhaps LA, maybe, Seattle, Cleveland, Washington, and Philadelphia, right? So you can do a bit of detective work to sort of map out how the path actually looks like, right? And then here it's already reached Drexel, and as we saw, it's not responding anymore, right? So in fact, let's pull up the internet to network map and have a look. Yeah, it very well looks like that, right? So I think, I'm not sure of that first hop, but it probably was somewhere here. And then remember, it went down to Kansas, Chicago, Cleveland, Washington, Philadelphia, right? So you can already map out that path here. You can also probably map out here. So if you see from Sydney, it went to Guam, right? And then where did it go from Guam? Probably along this hop to LA, I presume, right? So you can do a bit of detective work and sort of figure out those paths, right? So that's another observation. A third observation, let me just look at these numbers. Where do we see that? Okay, let's look at hop 17 and hop 18, right? So if you look at that first measurement, for hop 17, the measurement is saying 264 milliseconds. For hop 18, it's saying 241. How could that be? Shouldn't the delays keep increasing as we move further away? Can someone explain why that might be happening? Or has traceroute gone completely mad? Found a better path, possibly? But unlikely, right? I mean, if you look at these packets are being sent back to back. Certainly, Tom and Tim, your answer is correct, possibly correct. We don't know. But my guess is it's unlikely because the traceroute packets they're being sent almost back to back, right? So it's very unlikely the path changed. Possible. I'm just saying slightly unlikely. Joseph and Victor and Sarah, you are saying queuing. Yes, I think that is a more likely explanation. I would think. By queuing here, we mean, remember these packets are being sent at different instances, right? Let me go back to the slide. Right, so we send 3 probes, we do the measurement, then we send 3 probes a little later, right? So what's very likely happening is the probes that were sent to the further hop, they experienced lower queuing because remember the amount of packets in the queues is very dynamic, right? So the queuing delays can actually vary at a very small time scale along the network. So it's very likely what has happened is the packets sent to the next hop experienced less queuing at that time compared to the packets that were sent to the previous hop because for various reasons, the network dynamics dictated that the queuing was slightly greater somewhere along the path. Now we don't know exactly where. It could be anywhere along those paths, but that is a more likely explanation. Another explanation certainly is that the actual path may have changed. But as I said, I would go with queuing being the main reason. because the likelihood of paths changing at this level of, at this time scale is perhaps a little less likely, right? Tim is saying traceroute mentions 64 hops max. So yeah, that's, I mean, I think that is a fairly large distance, as you may think of. So I think in most instances, you would reach from any source to any destination within 64 hops. As you saw here, we could get from Sydney to Philadelphia within how many hops? How many hops did it take us? About 25 hops. So I think 64 is a fair estimate for most scenarios. I would think so. Of course, you could always come up with an edge case where it might take longer, but I think for the most part, that's what they decided to just give up. At some point, they have to give up, right? So 64 was thought to be a reasonable enough number. And yes, you can actually increase the, if you do a man on trace route, you'll find there should be an option to actually increase that manually if you really wanted to. Yeah, the max TTL. I think that would be it. Okay, so yeah, the end-to-end delays really is a summation of all of this, right? So what we looked at, what was at a single node, the earlier discussion we had, but remember this is just at one packet switch. So effectively the end-to-end delay is the sum of all of that. And this picture here is just showing you some measurements done along certain routes, and this is showing you the cumulative CDF effectively. And you'll actually be doing some of this in your first lab. So I'll kind of leave this at this, and you can explore this a little more in your first lab. So I think let's do a couple of quick quizzes now, and then we can wrap up with a short discussion on throughput. So how about you answer this question for me as I activate it? Let's see where you're at. Yep. I would go with the majority here because remember the propagation delay, where was that? It does not depend on the size of the packet, right? The propagation delay is the distance divided by the speed at which bits can actually propagate. So the propagation speed. So there's nothing here to do with the size of the packet. The transmission delay is the one which depends on the size of the packet, right? So this is always a nice trick question, if you may, right? Let's look at the next one. So by the way, this question presupposes that whatever we are considering the setup that was discussed in the lecture, because the accurate answer for this would really depend on how the router is actually designed, but just go with what we discussed when we talked about this. Yeah, thanks, Tim. There was a question here about labs. So there is no lab this week. Yeah, correct. I would also go with this. So again, as I said, this is purely based on the discussion we had. So we said a packet arrives. The first thing the packet switch does is it processes the packet, decides where the packet needs to go, tries to push it out on that outgoing link. If that link is busy, it needs to be queued. Assuming it's queued, it gets to the head of the queue, then it gets transmitted. And then once it's on the link, it propagates, right? So that would be the correct sequence. Yes, well done, everyone. Okay, let's now take 5 minutes and quickly wrap up. So there's not a lot to say here in terms of packet loss. I mean, the reason of this is simply because the buffers get full and then any incoming packets get lost. Now, the key here is what happens after, right? So if a packet gets lost, what happens? So now this really depends on the situation. So sometimes this packet may be retransmitted by the previous node. Sometimes it may be transmitted by the original source. Sometimes the packet may not even be retransmitted at all, right? So this is something we'll revisit a little later in this course as to how do we deal with packet loss. So let's just keep that aside. So the last thing to consider from a performance angle is the throughput, right? There's a question here, Michael. Did you just say retransmitted? So yeah, what I mean by retransmitted is if this packet got lost, there could be a setting where B could somehow figure out that the packet was lost and then it resends that packet again, right? So that's what I mean by retransmission. Okay, so what do we mean by throughput? So throughput is the rate at which bits are effectively sent from the sender to the receiver. So here we are really talking of end-to-end throughput. So remember, again, we have an application running. One endpoint is sending data, the other endpoint is receiving data, right? So over a period of time, what is the rate at which bits are being sent? So there are again two sort of, you could view throughput from two sort of angles. One is the instantaneous throughput. So at any given time, what is the instantaneous rate that is being observed? But something that's more interesting is the average, right? So over a long period of time, what is the, on average, what is the rate at which bits are being sent from the sender to the receiver, right? So the abstraction we'll use in these pictures is as follows, right? Again, we'll keep things simple. Now, of course, real routers have multiple links, of course, but here we are just considered with the end-to-end throughput, right? From a perspective of one sender, one receiver. So here we have a server. The size of the file it's trying to send is F bits. The link capacity here is RS bits per second. The bandwidth here is RC. Notice I keep using the term bandwidth, link capacity, transmission rate interchangeably. Pretty much means the same in the context of our discussions, right? So an abstraction we can think of to perhaps simplify the understanding is that we kind of use this fluid abstraction. So we assume the bits are effectively some fluid like water. We assume the links are effectively pipes and they're carrying fluid at the given rate, right? So there are two, in this particular setting, there are two things, two sort of scenarios. So one where the throughput of this link is less than that. So we kind of signify that by the thickness of the pipe effectively. So in this case, what do you think is the average end-to-end throughput? I don't have an answer here, so maybe you can type it in the Zoom chat. What do you think? Assume the server is sending a very large file. So what would be the average end-to-end throughput in this setting? Yep, well done, everyone. So it would be RS, right? So in this case, the server can push data at RS bits per second. Those bits will arrive here. And since there's no other traffic that in this case, the router is forwarding, it will push through all those bits effectively here, RS, right? So it's going to end up using less than the actual capacity, if you may, right? Because that's all that's being pushed in here. Now, how about this? When RS is greater than RC, what would be the end-to-end throughput? So yeah, correct. As all of you have answered here, this would now be RC, right? Because now here, this bandwidth is lower than this, right? So even if this, let's imagine this server starts pushing data here at the rate of RS bits. Now, of course, this router can only send out RC of those. So the if the server was indeed sending at this rate, they will, some of those packets are going to have to be queued here, right? Because the outgoing capacity is clearly lower, right? So yes, in this case, the end-to-end throughput would be RC. In this case, it was RS. So I think one of you did mention something about bottleneck. So this is exactly the point that I wanted to make here, that again, while this is a simplification, of course, in a real network, you would have multiple hops, not just 2 hops. But along that path, you will always typically have a link which is sort of limiting the end-to-end throughput, right? So in this example, it was this link, which was the bottleneck. In this example, it's this link, right? So there's always this one key link that is sort of limiting the end-to-end throughput, right? So generalizing that a little more, you could think of a scenario like this, where the server link has a capacity RS, the client link has a capacity RC. And imagine we are abstracting the entire internet by one link. So again, this is again a very simple abstraction, but imagine the global internet is being abstracted by R. And in this case, imagine there are, at any given time, there are only 10 connections that are being sort of transmitted over this common link here in the middle, right? So, and let's imagine all those 10 connections get an equal fair share of this capacity. So each of them is effectively going to get R by 10. So in this setting, the average end-to-end throughput for each of those connections will be the minimum of either RS, R by 10, or RC. Now in practice, you'll see that the core internet, all typically, again, this is all typical, not, you can't sort of say that for sure, but in most instances, R would be very high. Even R by 10, it would be very high. So very often it's either RC or RS that often becomes the bottleneck, right? So either on the server side or either on the client side is where we experience bottlenecks. Again, typically, not always, but that's just a fair approximation to make, right? So yeah, I think we are just about a couple of minutes more than what I intended, but hopefully that's okay. So we'll call it a day. I'm happy to stay online if you have any questions here in the chat. If not, have a great week. And I'll see you all either on Ed discussions or in the lecture next Monday. So have a great week. Do remember labs start next week. Bye. And I'll just close off the recording.